Welcome everyone back to today's talk in the Mult-Agent systems seminar series, which is held as part of the Mult-Agent systems group at the Alan Turing Institute. My name is Stefano Albrecht, and I'm one of the organizers of the special interest group at the Turing. And with these few slides, I'm just going to give you a little bit of context information so you know what we are doing, and then I'll hand over to today's speaker. So this started in early 2020. The idea was that the UK was historically one of the big early contributors to multi-agent systems research in the world. A lot of exciting research came from the UK and still is. But over the years, the research and the labs have become kind of fragmented and became a little bit difficult to see who's who and what's happening in the UK in multi-agent systems research. So the idea between myself and Michael Wooldridge, who is a professor at Oxford, was that it would be nice to bring the labs together and to understand what's happening in this space in the UK. So we had this big seminar or symposium in February 2020, just before everything went down in the world. And that was very well attended with more than 100 different people from the UK and Ireland, lots of different labs in the UK that specialize in multi-agent systems research, and also industry players and defense labs. And so that led to a few things. We had the symposium. We are now doing also the multi-agent systems seminar series online, and to give labs a platform to present their research and show the community who they are. We have this virtual labs Google map where we try to pinpoint all the major labs in the UK that specialize in one way or another in multi-agent systems research. If you have a lab that's not on the map here and you would like to be pinned on the map, then please get in touch with myself or Michael Wooldridge, and we'll add you to this map as well. And you can add meta information such as website and research focus and so on. And we have a mailing list, which is multiagent@turing.ac.uk. This is for any emails related to opportunities in multi-agent systems research, conferences, grants, jobs. So feel free to sign up and use the list for as a more local UK specific outlet for multi-agent systems opportunities. And there's also a few websites. You see one of them at the bottom of the slides here. All the videos and the talk series are recorded and put online and on our YouTube channel. So you can just go on YouTube and search for Turing multi-agent, and then you should be able to find it easily, and you can watch it. You can watch the talks there as well and share with colleagues. And lastly, one of the latest initiatives we did as part of this work is a special journal issue, which will be published in the AI Communications journal. So the idea here is similarly to what we were doing with the symposium and the talk. It's to give UK-based labs another platform to present their research and all the exciting work they're doing in the area of multi-agent systems. So the deadline is passed, and we're just going through the review process, and hopefully this will be completely finished and published in a few months' time. And we will then announce this on the mailing list as well. And I can already tell you we have more papers than we anticipated, and lots of really interesting research that's summarized in these papers. So I'm really excited about this and very, very much look forward to sharing this with the community. And in fact, we have one submission from today's speaker, and this is the perfect transition. I'm now going to hand over to the speaker. I'm very pleased today to have someone from Huawei to speak to us. Huawei, I think most of you will know who they are. Today's speaker is David Mguni. He's a principal researcher at Huawei Research and Development. I just read you the little bio blurb, where he leads the multi-agent team in London. His research interests lie within multi-agent reinforcement learning, game theory, and optimal control theory. Prior to joining Huawei, he had various roles within industry. Most recently, he was a senior researcher scientist at Second Mind AI, which used to be Prowler. And he holds a PhD in applied mathematics from University College London. So thank you very much, David, for speaking to us here, and we look forward to your presentation.
Thanks. Thank you, Stefano. Thanks for the invitation, and thanks to the audience for tuning into the talk. So today's talk is about solving reinforcement learning problems through non-zero-sum structures. And the idea is that typically when we think of a multi-agent system, we think of multi-agent reinforcement learning. We think of techniques and procedures to be able to tackle problems where inherently the system has many agents, and we would either want them to cooperate or to perform some task for us. But the idea of this line of work is to turn the question essentially on its head and ask the question, can we use multi-agent structures to be able to better address some problems in reinforcement learning? So essentially taking reinforcement learning and looking at it through a different angle. At the end of the talk, we'll kind of reconnect back to multi-agent systems, given multi-agent reinforcement learning is an extension in one way or another of single agent reinforcement learning. So again, thank you for the invitation. It's a great privilege to talk. The outline of the talk is, first of all, I'm going to discuss this two-player framework, which is this augmentation of the existing and standard reinforcement learning paradigm, and give some motivation for why we would want to kind of extend the formalism in this type of way. And then I'll go through some of the kind of core fundamental problems that we think that this framework might help address and one day be extended in different ways to be able to deliver higher performance in these settings. And then lastly, I'll reconnect back to the classic multi-agent setting where we have n agents, and show that actually if we add an additional agent or even an additional set of agents, then we might be able to use the same kind of principles that we did in step 1 in a multi-agent setting. And lastly, just to kind of give some theoretical fundamental principles, I'll describe some interesting properties and results that we've established to be able to put this on more theoretically grounded, firm theoretical ground. Okay, so limitations of current RL or reinforcement learning methods. So something that's well known is that there is an exploitation trade-off. So that means that to find the best policy or optimal sequence of actions, we have to explore, given that the system is unknown. But while we're doing so, we also want to maximize the rewards that we know are available to us, given what we've learned in the system. So inherently, these things can be in conflict in one way or another. So that introduces a trade-off. However, how to kind of systematically perform this trade-off is a very difficult question, and it's kind of a core fundamental question within reinforcement learning. The second thing is we may also, in an unknown environment, want to learn to find the optimal sequence of actions, but do so in a safe way, especially in environments where there may be some states in which we could actually end up in that will incur quite severe violations. And especially as machine learning and reinforcement learning algorithms become more prevalent in real world settings, this is becoming more important and more of a concern. Lastly, in the single agent reinforcement learning space, one thing that is interesting is tackling environments with sparse rewards. That means that the agent infrequently receives a signal from the environment about its own performance. And then the multi-agent setting, one thing that is quite common and at the top of people's minds is how do we optimize the performance by way of getting many agents to coordinate, especially when we're talking about systems with large numbers of agents. Okay, so our goal to be able to try and handle this these set of problems and ask the relevant question is to first of all develop an n+1 player formalism that can also drive selective exploration, and I'll go into what that means later, but where exploration is most needed. The second thing that we would like this framework to be able to do is help in sparse reward settings by perhaps manufacturing our own new reward signals that haven't come from the environment, but nonetheless could help guide exploration in a systematic way. The third thing would be that we can perform safe learning whilst also maximizing the set of rewards where safety isn't an issue. and hopefully use this formalism that we're now developing to try and extend it in many different directions, most of which what we love, which is multi-agent systems. So when we go into the multi-agent settings, we would like to kind of see this framework drive the policies to higher performance, and perhaps even give capabilities of learning in some settings where the payoff structures are a bit more complicated than, say, team game or zero-sum settings. Okay, so the first set of work that I'd like to talk about is DESTA, which is a framework for doing safe reinforcement learning. And this is kind of an application or an instantiation of this two-player formalism for a single agent setting. So this is work that's been done with various collaborators that you can see at the bottom of the slide. Okay, so just some background. So safe execution, excuse me, is critical in a vast number of applications. So the one that kind of comes to mind most easily is if you imagine autonomous driving, where of course it's extremely important that you don't collide with other vehicles and pedestrians and obstacles. So solving these tasks might require, in some instances, highly specialized algorithms that have been developed and engineered and fashioned to be able to solve the very particular features of these environments. However, having fashioned such algorithms to be able to solve these tasks, these algorithms may not be inherently extremely safe, which is what we might need them to be. And training, say, machine learning or reinforcement learning from scratch can be costly, and also kind of discard some of the usual specialized knowledge that we've introduced into these highly specialized algorithms. So the question that we asked ourselves is, can we develop a framework, like a plug and play framework, where we can incorporate the knowledge that has been developed in such highly specialized algorithms, whilst as well using reinforcement learning to augment the safety of these existing methods? Okay, so just a quick discussion on the background of how safety is often done in reinforcement learning. So safety is often tackled using a constrained Markov decision process framework. So this is essentially, you have your classic MDP, and then you also introduce a set of constraints which can be measured by way of some kind of violation, for example, safety violation, or a budget that you associate to your problem, which you don't want to violate. However, in using standard reinforcement learning algorithms, one thing to bear in mind is that in reinforcement learning, to be able to find the optimal policy, we typically perform exploration by introducing randomness. And randomness is a very important part of reinforcement learning. However, in a system in which you are seeking to keep the agent safe, random actions might inadvertently lead to safety violations. So there are some existing methods where we can manually engineer fixed safety recall actions, but quite often some of these things would require kind of manual embedding into the policy, which may be appropriate in some settings and may not be appropriate elsewhere. So taking a look at how nature does this. So within nature, there are lots of instances of which we see nature having safety mechanisms within animals. So one of the kind of common set of safety mechanisms are reflexes. So these are automated interventions that assume control of the system to keep us safe. So the one that I guess many of us would be quite familiar with, if we put a hand over a fire or something like that, even though we might have the objective to reaching into whatever's in the fire, the barbecue, whatever, the safety reflex will kick in. It will withdraw our hand and keep us safe. So this is an example that is in mammals and humans and other animals. But we also have other reflexes embedded into our safety systems, such as diving reflex. The crucial feature about these systems is that they will override whatever we were trying to do before in order to keep us safe. So our goal here is to develop a safety framework that only considers safety when it's necessary. And to do this, it will be, we would like a plug and play method So we'll be able to incorporate an existing RL algorithm or method into our framework, and then allow this to do complex planning about how to keep us safe. For example, we might need to take an action now to be safe in the future. And we want some other properties of this framework, such as convergence guarantees up to some point, and be able to kind of exploit some of the specialized knowledge of the algorithms that we're plugging and playing with. Okay, so what we did is construct a framework, which is a two-player framework, in which we decouple the objectives of safety and task. So what does that mean? That means that we first of all introduce a second RL agent, which we'll call safety agent. And we already have the original agent, which is we'll call task agent. The difference now is that safety agent purely has the goal of keeping the system safe, whereas the task agent purely has the goal of maximizing rewards. So these things are completely decoupled. Crucially, in this setting, the safety agent gets to override the actions of the task agent wherever it sees necessary to do so. So it will observe the proposed action of the task agent and then say, well, actually, I needed to perform an action to keep us safe here. It may be something that is required at this very point in time in terms of a safety violation in the next state. But given that the safety agent has its own objective, you can also do planning. So as to think, how could I take an action now to ensure safety in the future? So just as I mentioned, planning is quite important. And this is kind of a simple example of here on the left, we have an unsafe road where much further down the line, we might fall off a cliff. And on the right-hand side, we have a safe road. And although it's very important to make the correct decision of going down the unsafe path, we don't get the signal of whether the path is unsafe until much later on. So we have to do some planning. We have to take an action now to maintain safety. And so decoupling the objectives in this way is very useful, because one of the agents is purely allowed to kind of consider only the task of minimizing safety violations. Okay, so earlier I mentioned something about selectivity of how we consider where we should act. So crucially, at some states, there could be a conflict in terms of there's a high reward, but also it may be unsafe. And in this situation, if we had a framework that, for example, a Lagrangian framework, which bungs the objectives or rewards of safety and the task reward into a single objective, it might undermine the signal that we get about safe behavior or unsafe states. So we would like a framework that is selective about where it performs safety actions and only does so at the most relevant states. So the way this is done is that the safety agent has a criterion, which I'll explain a bit more, in which it evaluates whether this is actually a state in which it gets to, it should override the other agent, the task agent. And when it does so, it will pay a cost for that action of overriding. If it's not worth paying that cost, i.e. if it doesn't deliver additional safety, then the safety agent will learn, actually, I shouldn't be overriding the other agent, so it should be free to take its action, which will maximize. Otherwise, it will override. And another feature is that the safety agent uses a deterministic policy. This can be done in an off-policy fashion, so the safety agent can learn from the experiences generated from both players, i.e. itself and the task agent. Okay, so just to put this into context and in a concrete setting. So on the left-hand side, what we see is a policy that is inherently unsafe, but may be good at doing some fine-tuning motor control for an autonomous car. And so if we evaluate the safety of this policy, although it might be good at taking roundabouts and tight corners in a road that's heavily populated with other cars, other vehicles, this might cause collisions and safety violations, even though the policy itself is quite useful in certain instances. So what we did is take this controller and embed this into our DESTA framework. And we can see that what happens is the safety agent will learn to take control so as to minimize safety violations anywhere it might be at risk of colliding with another car. So in that setting, this is when the task agent policy is pre-trained. So we're taking an expert policy and augmenting the safety for that. So now we would like to kind of tackle the setting of where we have a task agent that also needs to learn its policy, as well as a safety agent that also needs to learn its policy. So to do this, we looked at kind of standard RL benchmarks for safety, one of which is Lunar Lander. And the interesting thing about Lunar Lander is that there are a set of states, a very few set of states, where actually safety is relevant. And in this way, it's a perfect way of testing whether we would be able to improve safety, but whilst also ensuring that we get still high return. So as you can see in blue, which is our DESTA framework, our evaluation return actually becomes higher when we use this framework, presumably because at the set of states where safety is not a concern, the task agent can get to the, can perform the task, which is landing in between the two flags, in a very smooth fashion. But if we're in danger of landing in the unsafe zones, which is outside of the two flags, the other agent, the safe agent, will intervene. And with these interventions, we can see also in blue in the evaluation cost and the training cost that this framework DESTA would then lead to lower safety costs and lower safety violations. Okay, so another setting that we'd like to look at is, which is also a standard RL benchmark, is Frozen Lake. It's quite a relatively simple environment, but the useful thing about this is that it can test whether we're able to do safe planning, so be able to take an action now to maintain safety. So the schematic of the environment is on the right, and essentially we have to form a route from the top left to the bottom right without going into areas of the lake, which would be dangerous for us. Importantly, using deterministic actions is crucial here, because inadvertent randomness or exploratory actions near these unsafe states could land us into trouble. So having a deterministic intervention policy is quite useful here. And again, we see that we're able to maximize return whilst at the same time reduce the safety violations as well. So ours is DESTA-SAC. So the take-home message is a framework that decouples safety and planning, but we approach it as a two-player game, so it takes on the characteristic of a multi-agent framework, even though the problem is inherently a single-agent problem. So this enables us to try and minimize safety violations, whilst at the same time maximizing the environment reward at all other states, and doing so using deterministic interventions where necessary. As we saw in the autonomous driving example, we can take already pre-trained expert policies that might have been very well crafted and suited for a particular setting, and augment the safety of those policies. Okay, so the next framework that I'd like to discuss is another setting, which is the framework adopts a very similar characteristic, although the problem is very different. And this is the trade-off between exploration and exploitation. So exploration at a glance, so there's various ways of performing exploration. And one of them, and one most popular approach, is just to essentially inject some noise or randomness into the policy. So I may have started off with a deterministic policy, but the idea is that if I execute some action with some probability of being random, then I will be able to eventually explore more of the state space and find the optimal sequence of actions. And there's various ways of kind of introducing this noise, some of them very sophisticated. There is also a second way that we might drive exploration, and that is through curiosity-driven exploration. And what this essentially means is that we're going to introduce an intrinsic reward, and that intrinsic reward, so i.e. a reward that is not from the environment, but something that we've introduced ourselves, which rewards the agent for exploring in areas of the state space which haven't really been seen in one way or another. So you can either use a prediction model or a discrepancy between some estimate to be able to say that I haven't seen this area of the state space, reward the agent for going in that direction. So these approaches couple exploration and exploitation, so they can these two objectives can kind of interfere with each other. On a similar way, we can also use uncertainty quantification. So how uncertain am I about this area of the state space, and use that as a kind of intrinsic reward to drive exploration. So crucially, here again, we have this characteristic that the exploration and the exploitation objectives aren't fully decoupled. So what we would like is to kind of use our two-player thinking in a way that will be able to decouple these objectives so that we can do advanced planning, not only for maximizing our rewards, but advanced planning so that we can think about where to take exploratory actions now so that we end up in areas of the state space that we haven't yet seen before. We'd want this framework to also have useful features like convergence guarantees, and also crucially only perform exploration at the set of states where exploration is important, and leave the agent to be able to maximize the task reward or known rewards elsewhere. So much in a similar way to DESTA as we previously saw. So here we can decouple these two objectives and assign one of the objectives to one agent, which we'll call the explorer. And as the name suggests, the explorer is seeking to minimize system uncertainty or maximize kind of some exploration criteria, which we're free to define. We can just plug in any kind of reward that will serve as an adequate notion for exploration. And similarly, the exploiter just simply takes the reward from the environment and seeks to maximize its cumulative rewards. So as before with DESTA, here in this framework, the explorer gets to override the exploiter, but crucially, as before, it pays a cost for doing so. So only would learn only to explore when it's profitable to do so, and then leave the other agent to exploit wherever it's not profitable to explore. So we've run some experiments and shown that actually this is very useful if we're taking some standard RL algorithms. So we've taken soft actor critic or SAC, and then plugged this in this two-player framework and generated what we've called SEREN-SAC. And we also did this with PPO. And we showed that in the vast majority of cases, we're able to perform more efficient exploration and sometimes even derive just an overall higher performance, with the exception of Reacher. Reacher is somehow a complicated setting, which we want to investigate that a bit more. So we did this in multi-agent Majoko, and we also did this in a simple grid world setting where we took DQN, which is a discrete or finite space settings, and then augmented DQN with our framework SEREN to construct SEREN DQN, and we got this boost in performance. So next, I'd like to move on to our next application or instantiation of this two-player framework, which is learning to shape rewards with a game of two partners. So the idea here is that we'd like to address or look at the problem of sparse reward settings in reinforcement learning. So just a little bit of background. So reinforcement learning offers us the potential to learn autonomously and without the need for human input or intervention. This is one of the remarkable elements of reinforcement learning. However, central to the success of reinforcement learning algorithms is feedback, rich feedback about how well the agent is performing. But it just so happens that there are many settings that don't provide that rich feedback. They don't provide informative signals, and they may just provide a signal of whether you've won or lost at the end of the episode. So this is what we would call a sparse reward setting. And this becomes very, very difficult in terms of sample efficiency, given that the reward is so central for learning where is it that this action was beneficial and where it was not. So given that RL algorithms generally require, so here is another example of where they generally require, so specifically Montezuma's Revenge, where throughout the state space, you can see that the agent isn't getting any kind of reward signal unless it reaches the key. So one way of kind of handling this or helping this problem is by introducing an artificial or an intrinsic reward signal, which we call a shaping reward. So we just construct some function which we call f and introduce that as a function of the state. So if we have knowledge of the environment, then this is great because we can somehow embed this into our construction of f. But this would obviously not be appropriate when we don't know anything about the environment, because then we won't be able to exploit that information in our construction of f. So our framework and our question that we're asking is, can we construct this function f on our own? Can we introduce new reward signals that will help guide the agent in an appropriate way to be able to more efficiently learn the optimal policy? And to do this, we again introduce a second player. And the idea of this player is to make an observation of the state and then introduce an additional reward. And the way it does introduce this additional reward is by essentially taking an action, but this action doesn't affect the environment. This action simply is a signal that is injected into the agent's objective that is perceived as a reward in the same way that an environment reward is perceived. So the original RL agent's objective now looks like this equation. So we have the reward from the environment, R, but we also have this new term F, and A2 is the action of this additional player, this shaping agent. And we've got noticed the time indices, and that will be important later for ensuring that we preserve the optimal solution of this problem. So in a similar way that we were describing before, we don't want to add at each and every single state an intrinsic reward or this shaping reward. And the reason for doing so is that there may be a vast number of states where actually it's irrelevant whether the agent receives an additional reward signal or not. If the reward signal is already rich at that state, it's not worth learning how to add an intrinsic reward at that state. So a better way is for this additional agent, the shaping agent, to learn which set of states adding a set of intrinsic reward is useful. And so the way we do this is to add a switch, which essentially the additional agent learns to switch on when it feels that it is useful to add an additional shaping reward. And that switch will stay on until either stochastically or probabilistically, or the agent decides to switch it off. So this kind of reduces the complexity of the shaping agent's problem, because now it's not learning how to add additional rewards or the magnitude of those rewards at each and every single set of states. So just a very simple example of this, and I won't dwell on this because it's quite intuitive. So if we have a simple maze environment on the right-hand side, let's go to that straight away, where we start at the bottom left, and we have an optimal goal state at the top right, but we also have an additional quote-unquote goal state, which we've defined as safe, where the agent receives a reward, but it's a suboptimal reward in comparison to the one at the top right. The agent's goal is to learn how to get from the top left to the bottom right without being kind of suckered into the safe state. So what we see, even though this is an extremely simple problem for reinforcement learning, it will learn how to get to the optimal state eventually. What we see is that this additional agent learns to introduce rewards where you see in dark green. So only at the set of states that essentially guides the agent to this optimal goal state. So just some features of this framework. So what this framework does is it learns stable policies. So the additional agent is eventually converging to a policy, and it does so quite quickly because it is only learning a subset of the set of states. and it's also guaranteed to converge. And we showed that it preserves the optimal policy, which is very useful. You don't want the intrinsic reward to suddenly take over and guide the agent to do something strange. So this is pretty much formalizing what I was saying before in terms of learning the set of states that are useful to add new rewards. The equations here just simply say that we can actually characterize the points at which these intrinsic rewards should be added. So there's a specific condition that we can evaluate online and determine when that this shaping reward should be added, and then this when we should switch on these intrinsic rewards. Okay, so the take home for this is that this is an automated reward shaping method, and it doesn't require a priori human input, so as to engineer some intrinsic or shaping reward function F. So the two-player framework is one in which the shaping agent, this additional agent, and the original agent perform concurrent updates, and that's quite useful because now we learn quite efficiently. But even though it's kind of two players learning at the same time, we still have convergence guarantees. And this switching control, or learning exactly which set of states we are going to switch on and activate these shaping rewards, and we're going to switch off, it reduces the complexity of the problem. And what I mean by that is that we only need to learn the optimal magnitudes of these intrinsic rewards at a subset of states. Okay, so as promised, I'll now circle back to the multi-agent setting, where we can take some of these ideas and techniques and put them in a multi-agent context as well. So just a bit of background, which I'm sure many are familiar with. So the idea of cooperative multi-agent settings is to allow a set of autonomous agents to solve various tasks. And one example would be autonomous driving, and another would be swarm robotics. So unlike a single agent setting, in a multi-agent setting, finding the optimal policy, the joint optimal policy, is the task. So the joint optimal policy would be the optimal policy for a set of agents. Unlike single agent settings, often what is required for the agents to successfully solve the task is coordination. So consequently, agents have to base their decisions not only on what they perceive as being their optimal reward, but also the other actions of other agents. And because of this interdependence of other agents' actions, it becomes extremely expensive, and even for moderately sized systems, and even become intractable to solve such systems. So because of this, sometimes multi-agent reinforcement learning methods can suffer from poor performance if we don't adequately account for the behavior of other agents, or we don't coordinate. Sometimes we also have to restrict ourselves to idealized scenarios. This isn't so much of a problem in a team game setting or cooperative game setting, because we can we've got many tools to be able to solve team game settings, reward structures of that kind. But if we start to deviate from that, then we become a bit limited in what we're able to do. And a crucial problem is scalability. If we now need to take account of other agents' actions, then the system becomes exponentially complex, so computational complexity. So one of the ways that we help we sought to help address the problem of coordinated learning and performance is by constructing a method that would introduce intrinsic rewards. So this is quite very much an extension of what I showed you before in our framework, where we had a two-player framework with intrinsic reward settings. So as I mentioned before, coordination is a major challenge in multi-agent reinforcement learning, to be able to learn the optimal policies or optimal joint policies. But also we have inherited features such as sparsity, reward sparsity, and multi-agent settings. So we still have those features that we need to overcome in a multi-agent setting. So much like what we did before, we now introduced another agent, which we call the generator, that introduces reward signal for the other agents. So we're thinking about a team game setting. So there's inherent symmetry or homogeneity, so in the way that we can introduce this additional reward. But crucially, now this generator, this additional agent, which is constructing this additional reward for each of the agents, has a term, this L term, which we're seeing in the first equation, which plays a very special role. This L term is one in which it is rewarding this generating agent, this additional agent, for encouraging the agents to perform joint actions that haven't been performed previously at less known states. So unlike in a single agent setting, we need to encourage coordination, which may involve encouraging the agents to take joint actions that they've never taken before, to see if those joint actions lead to the higher payoff. And what this generator is then encouraging the agents to do is precisely that through its intrinsic rewards. So in the second equation on the bottom left, this F term, parameterized by theta, is what the new agent, the generator, is introducing. And I is this idea of having a switch on and off, which we saw before in the single agent setting. This system is kind of driven, the exploration is kind of driven by the generator in pretty much the similar way that we saw before. But now the goal of the generator is also to encourage coordination amongst the agents. So we tested this apparatus in some benchmark multi-agent reinforcement learning environments. So on the left, you see LBF, which is level-based foraging. So simple task where the agents have to find apples, but crucially in some of the apples, they have to coordinate to be able to get the reward. And if they don't coordinate, they will receive a negative penalty or penalty. So what we see in blue is this framework, which we call LIG, with some reinforcement-based learner. So this would have been PPO. And we see that this augments PPO over the orange line to be able to give a maximal rewards. So we've tested this in a number of settings in LBF. And on the right-hand side, we see some selected StarCraft multi-agent challenge maps as well, where we saw significant boost in performance. Okay, so just, I don't know, this is quite a lot. So just another kind of application or instantiation of this framework is the idea of learning quickly when in instances where we can use some other form of reinforcement learning to learn quickly, and learning slowly and more patiently when it is warranted to do so. So I'll justify these kind of terms in a second. So multi-agent reinforcement learning is expensive due to the fact that we need to take into account other agents' actions so as to find the optimal policy. So finding it involves kind of sweeping through each possible joint action, essentially, and this is quite an expensive operation. So with increasing number of agents, this becomes more and more expensive and sometimes prohibitively expensive. So, excuse me, so centralized learners are one in which we have a critic which observes the joint action or the behavior of all other agents. And this is extremely useful in environments in which the behavior of other agents is critical for us reaching optimal policy. But like, for example, in the intersection problem on the left-hand side, but it can be unnecessarily expensive in settings where actually it doesn't really matter what the other agents are doing. I just need to kind of move in this direction and I'll be fine. There's a setting there. So it can be unnecessarily expensive in some settings or some regions of the state space, but also extremely crucial in other regions where this kind of interdependence of our other agents' actions affects our performance. So on the other hand, decentralized learners are reinforcement learning methods or multi-agent reinforcement learning methods that have a critic that does not explicitly account for the behavior of other agents. So the advantage is that we can just learn whilst ignoring the behavior of other agents, and this can be extremely fast and computationally inexpensive. And so there is a great paper that outlines the fact that in some Starcraft multi-agent challenges maps, actually independent learners do extremely well. However, the question can be asked, is independent learning then all that we need? And the answer is actually it's a bit more nuanced than one or the other, in the sense of, if I simply ignored the behavior of other agents, then this can happen. I'm failing to coordinate with the behavior of other agents, and therefore not finding the optimal policy where my actions take into account their actions. It's a kind of mixed pattern where we can see some settings the independent learners do well, and some settings where the centralized learners are necessary. So we can summarize the advantages or disadvantages, broadly speaking, in terms of computational expense, but also in a centralized learning, it has the advantage of really being useful for coordination, as well as providing stronger convergence guarantees. We can kind of incorporate centralized training into a framework where we have a critic that is centralized, but also we have a policy which is decentralized, and this is called centralized training and decentralized execution, which somehow synthesizes these two learning methods. But of course, we still have the drawback of the computational complexity for the critic whilst we're training. So our idea here is to be able to construct a learning framework that actually has both centralized and decentralized settings, learners. So, I mean, it's quite easy to think of a kind of setting in which at the beginning, it would be useful to use decentralized learners because it doesn't really matter what the other agent's doing. But in some area of the state space actually is very important, i.e. at the intersection, to figure out and take account of the other agents. So why not kind of have a setting or learning method that synthesizes both of these useful learning methods? So crucial to doing that, of course, is to determine when to use centralized learning method, which I'll call C, and when to use a decentralized learning method, which I'll call D. So to do this, we introduce another agent, of course, and this other agent kind of learns when to switch between these two learning methods, and does so favoring decentralized unless centralized delivers some benefit, in which case we can reap the benefits of fast and computationally efficient learning of decentralized learning whilst switching to centralized learning where necessary. So similar to before, we can kind of evaluate or construct an expression which characterizes exactly when we would need to perform these switches. And this enables this switching agent, given that it's only got two actions, either switch to C or to D, it can learn very quickly how to perform these switches whilst the other base learners are kind of learning themselves while interacting with the environment. So our framework, which we call MANSAR, is almost like a new alternative to CTDE because it synthesizes centralized training and also decentralized training as well. So the take home is that we induce fast and efficient learning, and where the information is local and sufficient, but it also is intended to eliminate the catastrophic failing of decentralized learning by switching to centralized learning within where it's required, and also try to kind of leverage the advantages of both of these frameworks, whilst kind of avoiding these drawbacks where we have to, in centralized learning, introduce structural assumptions to be able to be tractable when the size of the system is large. Okay, this concludes the end of my talk. I hope you enjoyed it very much, and I'm happy to take questions if we have time. Apologies if I've gone over slightly as well.
No, perfect. This is good timing. Thank you very much for this super interesting talk. I've got some questions, but I think I'll hand over to the audience first to see if there's any questions there. So feel free to just unmute yourself or use the hands feature. Don't be shy. anyone from the audience with questions? Okay, I think I'll get started with one question. So I'm very interested in a lot of the works that you've showed here. Early on in your presentation, you talked about the safety problem and where you were training a safety override policy. So I think that's a reasonable approach, and I've seen a few papers, where they all kind of think along those lines. But in your case, the override is also an RL agent. So my question is, who ensures the safety of what the override RL agent is doing? Right. So for example, in the first set where you override the driving policy, I mean the new guy, who's making sure that the new guy is driving safely, right? Is what I'm wondering.
Yeah, thanks for the question. So the idea that we're trying to kind of introduce here is that this new guy having only the objective of safety, then its policy will be kind of curated or tuned towards that goal. So some of the previous approaches where one might have a single objective that houses both safety and the task reward states where there's a conflict between your reward and safety, then you may actually end up performing an action that doesn't really do well by either of these criteria. But the idea is that because the additional agent is a reinforcement learning agent, and its only signal is the safety signal, it should eventually learn these are the set of states that I need to take this action to be able to ensure safety.
Okay,
yeah.
but we that's a hope that the new guy is behaving safely, right? With this new signal.
Yeah. I mean, we're relying on reinforcement learning processes to ensure that, or to help us guide this agent towards a policy that learns the safe actions or the safe policy. But I think the central idea is that because it's receiving like a pure safe signal from the environment, provided that the environment provides that signal that this is a bad state, then eventually, given that reward and given our reinforcement learning process, eventually we should see that this agent should be able to learn a safe policy, provided that the assumptions of reinforcement learning are satisfied.
Okay, thank you. Any questions from the audience? We've got a hand from Sam. Just feel free to unmute yourself.
Hi, can you hear me?
Hi, yeah.
Yes.
Yeah, thank you for the presentation. It was really interesting. I was wondering something about the ROSA work you presented and the where you have the shaper agent that is getting this sort of a learning and shaping reward function. And I was trying to understand like to understand why it's actually helps in that case, because it seems like it's selecting states along that were previously visited that by the main agent, and gives them a reward shaping an extra reward bonus. But wouldn't that be the job of the critic or whatever part of the normal agent that is trying to estimate the value function? Like, wouldn't the value function do this already? Like, how is the shaping agent helping in this case?
Yeah, thanks. That's a great question. So I think in sparse reward settings, because we're not receiving any reward from the environment, even a critic wouldn't be able to necessarily say this is a useful state to be in, because there is nothing from the environment that's telling us this is a useful state to be in. Of course, one would expect eventually the value function, as it gets closer to optimality, to be able to learn that. And of course, once we have converged to the optimal policy, that value function should reflect that. But during the course of training, if we have an extremely sparse reward signal, then we don't get anything to kind of guide us about whether this is a useful state, whether we should be exploring in this region. And so the idea of kind of shaping rewards was to somehow help that learning process by introducing new reward signals that will help guide it. I mean, I guess there's two parts to this question in the sense of, firstly, why should any kind of intrinsic reward be useful? And then the second one would be, why should our framework, where we have another learning agent, be useful? Because this learning agent, after all, is learning. The answer to that part is not something that's actually well shown in the slide, sorry about that. But the answer to the second question is that the second agent, we really simplified the action set for this second agent. So the second agent can either add a reward signal, let's say 1, or decide not to add a reward signal, so just do nothing. And the idea of that is that even in this simple setting, if we have like for example, a trap, this suboptimal state, what we can do is learn to just add this simple reward signal that will guide the agent away from this trap state. And that's something that's quite hard to do if you don't have some additional intrinsic reward that's guiding you away from that state.
Okay, I guess like my question then is that for the shaper to decide which state have intrinsic rewards or bonus rewards, it needs to, like, the agent needs to have achieve the reward at some point somewhere, or how does it actually decide the states? Because in the classic RL setting, you would get the reward by chance, even in the sparse reward setting eventually. And then the job of the critic is like to sort of backpropagate that through the trajectory. But how do you get the signal when there is no signal?
Yeah, indeed. So I think it's partly to do with the fact that with the shaping agent, with the shaping agent, it has this, I'll show it in the multi-agent setting because it's quite similar. So with the shaping agent, it also has its own objective, and this objective includes some of the term which rewards exploration. So the kind of question would be, why can't we just introduce this exploration bonus straight away into the objective of the original reinforcement learning agent? We can do that, but what ends up happening here is that this additional agent is able to do quite kind of, let's say, complicated things. If it's trying to guide exploration in a certain region, it might be able to plan to say, let's say, if I guide you here by a little bit, then I know later on you'll end up in some other region of the state space. So I think we have some level of intuition about why this would outperform some base learners. But I agree, it's kind of quite difficult to really crystallize exactly all of the instances where this would be better. But I think the overall question about sparse reward environments, I think is quite difficult for reinforcement learning algorithms alone in sparse rewards to efficiently learn. I mean, ultimately, if you have a finite state space and sufficient exploration, you expect the agents to eventually reach the optimal value function. But the question is can I do so efficiently? And I think this is where this framework is supposed to help us here.
But then do you think that it's that like you're achieving this better, essentially, like value estimation for each state because you have more capacity with the extra agent, or because you get agency in the critic, essentially? Because for me, I kind of see it as like a more powerful version of a critic, this shaper agent. I don't know if you agree with that.
I mean, I guess what I'm trying to get at is that the critic is somewhat limited in how it can appraise a set of actions, because that is only being determined by the reward from the environment. But what this framework is, what we're suggesting that this framework is able to do, is that it offers essentially a new critic the flexibility of being able to generate, or let's say, positive appraisal for a certain set of actions even by not being restricted by what it's received from the environment. So this is like, for example, if I were to try and discover a sub-goal, which along the path to that sub-goal, I didn't get any kind of reward. This might be quite difficult to naturally reward the agent for sub-goals that aren't necessarily provided by the environment, that decompose a very complex problem. But if we're able to be more flexible in the way that we introduce rewards and appraise certain actions, then we can generate kind of artificial sub-goals that will enable the agent to kind of decompose very complex tasks. So this is kind of behind some of the thinking that it unleashes the critic or the value function to be able to do more than simply appraise what has actually been happening in the environment, if that makes sense.
Yeah,
sorry, Sam, I think I'll have to cut off because we've got a few more questions lined up and I'm conscious of the time. Sorry, just to move this along, we have another question from Farzaneh Farhadi. If you can unmute yourself and just read your question yourself, I think that's better than me reading questions. Person not here anymore. Okay, I'm not sure if the person is left. I've got more questions posted directly to me for you. One by Che. I don't know if Che is still here. Yes, Che, again, do you want to maybe ask your questions yourself rather than me reading them? Okay, well, maybe I read the question then. One question is, does the introduction of new learners impact in any way the latency of the overall system in producing the required action in a timely manner?
Yeah, it's a great question. I mean, I guess the introduction of a new learner might then suggest that we've kind of operated a more complex framework. But the idea would be that we've got concurrent learners. So the safety agent and the task agent are learning concurrently. What is true that you have a two-player system, and that might suggest more complexity, but it's not as extreme as you might imagine because only one of the players gets to act at a single point in time. I think I've got the broad understanding of the question, but yeah, I think that might be an answer to the question, but if not, I'm happy to elaborate as well.
Well, I can't tell because I'm reading the question off the list here, but Che, feel free to unmute yourself if you want to follow up. In the meantime, I'll read the second question. In the setup where learning is sparse, would it be a viable alternative to the introduction of new learners if we were to try and interpolate between two neighboring states to create new information related to unforeseen states created by the interpolation process? Yeah, does that question make sense?
So I kind of got the overall gist of it, but I was not, I'm not 100% clear about the interpolation process.
Che, do you want to unmute yourself to clarify? Okay, well, I've not been hearing responses. Maybe Che's not listening in currently. But anyway, I think we've run out of time. So thank you everyone for asking questions. Also, thank you again very much, David, for a really interesting talk. And I look forward to talking more with you subsequently as well. Thanks everyone for attending. And we've got more talks lined up in the coming up presentation sessions. And you'll hear from us soon in the mailing list for announcements. So thank you all and see you next time.
Thank you. Thank you.